Okay, so just to start off with our log review today, we have our first definition, the most important definition we'll have all day. If you understand this and how to rearrange it, you can really get through most of the problems. Or like any difficulties that arise, this is always like the break glass case of emergency piece. You can always switch forms and just look at an exponential. Okay, so for the definition here, if x is greater than 0, that'll be the argument of the logarithm. And if b is greater than 0 but yet not equal to 1, b is called the base number, then the y equals, we read this as log base b of x. Okay, y is just a variable. B is the base of the logarithm. We'll talk about more about what that means. X would be the argument of the logarithm, the thing inside the logarithm. So as we can see, you're never going to be able to take the log of a negative number. If you ever ask to take the log of -3, the answer is always undefined, not possible. You also can't take the log of 0. It's undefined. You can't do it. So when we graph them, and next time I see you, we're going to have a vertical asymptote, right? Because it's just got a bunch of undefined stuff. But if you can write y equals the log base b of x, that's true if and only if. So an equal sign basically. If b raised to the y power equals x. Okay? So the base of the logarithm becomes the base of the exponential. Kind of nice how we use the same word both places. What was by itself is now the exponent, and what was inside the logarithm is now by itself. There are lots of ways to remember. Some people use like this sort of like wheel arrowy thing, but I can never remember which way it goes, so I don't use it. It doesn't work well for me. I always think of it as the base becomes the base because they're both called bases. That seems kind of obvious. I shouldn't say obvious, but it is. They're the base. But here the y is all by itself. Here it's got a friend. Here the x has a friend. Now it's all by itself. Not very mathematical, but that's the definition. So the first thing we want to do, and a lot of the problems you'll look at tonight, are just going to be switching forms, right? You have your logarithmic form. You have your exponential form. Okay? Usually if one of them is kind of a dead end, if you switch forms, it tends to be helpful. Just as a good kind of a basic trick. So for example 1, if we switch forms, we have y equals the log base 7 of x. Okay, well, 7's the base, so for the exponential, 7 will be the base. Y was all by itself, now it will be with the 7. X was with the 7, now it will be all by itself. So those are equivalent expressions. Okay, it just depends what you're doing as far as which one's easier to work with. Here, if you want to, take a minute and try B and C, and then we'll come back. Okay, so let's take a look here. So the second one is we have 6 to the x plus 2 power equals y. Here x plus 2 is still the exponent. The exponent can be an expression, right? It will be a lot. It makes it more interesting, right? It gives us more options. So here, the base of the exponential is 6. So I'm going to write log base 6. And again, the base number is a subscript. So if you're trying to type the math, you have to do the little subscript thing. And then now, the part, either the x plus 2 or the y is going to go behind it. But since the x plus 2 was with the 6, now it won't be, but the y will be. So we'll say log base 6 of y equals x plus 2. Okay, y is regular size. So log's regular size, subscript of the 6, y's regular size, x plus 2 is regular size also. And again, we're just switching forms. We'll see why we might want to do that at times. Here for C, we have 7a equals log base 5 of x plus 2. Okay, well it's going to be, the base is going to be 5. 7a was by itself, away from the 5, so now it gets to be on the same side as the 5. And then x plus 2, which was with the 5 inside the logarithm, is now by itself. Okay, any questions there? So here are some properties that we need to be aware of, and these will come up quite a bit. It's kind of our logarithm toolbox. It can help us evaluate things and get some answers here, would be that, again, the base has to be positive. It shouldn't be 1, because if it is, it's not interesting at all. X is greater than 0. Not a great definition because there's never an X in the whole thing, so I don't think I really needed that piece. But so just to note, log base b. So base could be any positive number, right, besides 1. If you have the log of 1, the answer is always 0. Now, if you switch forms, that makes sense because you get b raised to the 0 power. We know that equals 1. Next property, log base b of b is equal to 1. Well, if you switch forms, you get b to the first power equals b. Kind of makes sense, right? Here, the log base b of b raised to the y power is just going to be y, because b raised to the y power equals b raised to the y power. Be the same thing. This one's pretty strange looking. Now, it does come in handy when we solve equations, though. If you have a base raised to the log base b of y, so notice the base number here of this is an exponential, but in the exponent is a log base b, those will cancel out and you'll get y. Okay, in terms of the form here, if you wrote this out just to kind of justify it, you'd write it because it's an exponential now, correct? So this b would go here, this y would go here. So again, this went here, that went there, then the exponent would be over there. So kind of strange looking, but it's a property that we need to know. This wasn't on there, but the log of 0 is always undefined. You can never take the log of 0, because you're saying b to some power equals 0. Well, if you have a positive base, it's never going to equal 0. You know that. If you have the log base b of a negative constant, right? If it's negative x, you might have to do some work. And, it's a variable. It could be negative, and then a negative would be positive. But if it's a negative constant, it's always going to be undefined. Right? Because if you think of exponentials, if you have a positive base, which we said b always has to be positive, no matter what power you ever take it to, you're always going to get a positive answer. The other kind of things that would be good to put here, since we're talking about properties, is that if you see a logarithm with no base, that's called a common log. And that has a base of 10, but it's written as just log. Right? So on your calculators, there's a button that says log, and that is because it's a base 10 logarithm. If you're doing arithmetic with large numbers and you're using logarithms, the common log is really your friend. Now, what's much more important to us in here is called the natural log, which is base e, and that's written as ln. It's an L, though. It's not an I. It's ln. It's like Logarithmus naturalis or something in Latin. That's why it's, the L comes first. That's base e. That's a natural log. Super useful in calculus. All the logs that we do, we're going to start with natural logs and kind of figure out how to work with other ones, common logs included, as we go on. But the natural logs, because its reciprocal would be e to the x power. Those are both really important functions and actually really easy functions for us to work with in calculus as we get going. Okay, so we have some evaluate by hand here, logarithms. So we have a log base 3 of 81. Okay, and a lot of times with logs, when we go to graph them, it helps to know these kind of basic ones. One strategy, if you get stuck, is you could say like equals x and then rearrange it in exponential form to kind of give yourself a better idea. So what you could do, again, is if you're stuck on these, a lot of times it's helpful to write that out. Right, log base 3 of 81 equals x, or whatever your favorite variable is. Right? And then you switch forms, you get 3 to the x power equals 81. That's really what it's asking you here. 3 raised to what power gives you 81, and we all know what that is, right? 4. Yeah, so that's 4. Now, If you have the log base 3 of 80, you can't do it by hand. You just know it's a little bit smaller than 4. Right? There's only certain ones you can do by hand. That's one of them. Here is the log of 10,000. Now you might initially think, hey, where's the base? Well, it's a 10, so it's there. So it's saying 10 raised to what power gives you 10,000? 4. And you can actually just count the zeros. That's all you have to do. So that would be 4. There's like a pattern here, kind of. See if it continues here. The common, or the natural log of of 1, not e, the natural log of 1, that you might remember from our definitions, anytime you have a 1 inside the argument, the answer is 0. If you do get stuck, though, you can say, well, let's see. The natural log of 1 equals x. So that would mean e to the x power equals 1. Okay, that would mean that x must be 0, right? Because the only way you're going to get 0 out. You're only the way you're going to get 1 as an answer when you have an exponential is if you have a 0 power. So that would be 0. This one, when we learn the next properties, it'll make it easier. But here sometimes you could just sort of goof around with them and kind of see what you get. Okay. So say you have to do this one. We know what we know now. We know it's a common log, correct? So let's go ahead and just say, all right, let's set this thing equal to x and see what we can do. See what kind of trickery we have here. Well, I know this is going to be 10, correct? So I could say 10 to the x power is 1 over the square root of 1,000. Well, if I could get both sides to be a base of 10, right? If 10 to the x equals 10 to the 5th, then x would have to be 5, wouldn't it? It would be done. So let's kind of work towards getting the same base on both sides. So here, this is 1,000, and this is a square root. So 1,000 is 10 to the 3rd, and a square root means that you put a 2 at bottom. It's a rational exponent, correct? We're all okay with rational exponents. That's equivalent. Now, I sure wish this base was up in the numerator, but we know for our exponent rules that we can move the base. We just take the opposite of the power. So you could get 10 to the x, I kind of forgot the x, didn't I, is equal to 10 to the negative 3/2. So the answer is negative 3/2. And you could check that on your calculator if you wanted to, or whatever, but that's how you would do that. Okay, maybe we'll keep this problem. When we learn our next set of properties here, there'll be an alternate way that we could work that out. But kind of is again, so your fallback, I don't know what to do, I'm stuck, is if you have to evaluate, set it equal to x, try to switch forms, and see if you can make sense of it that way. So that's always the kind of last resort is just to try to do that. See what all right, so some properties of logarithms, and this is on that last example I mentioned that we might use these to kind of make things easier on us. We use these quite a bit because what it'll allow you to do is it mentions condense, which is like take a bunch of logs and make it into a single log, which is really useful when you're solving equations of logarithms. And then also we'll expand where you take one gross looking logarithm and make it into a bunch of simple looking ones. That's really a great thing to do when you're going to have to perform calculus on logarithm. So both these skills are really important to the point where expanding a logarithm before you try to take the derivative, when we get to that, it might save you 15 or 20 steps, like significantly less work if you know how to do this. What this is, these properties, r and s are just two things multiplied together here, r divided by s, or r raised to the c power. Notice in all these bases are the same, right? So if you have a base and it splits, and you get the same base over, we're not really going to see them work together like that. But what this says is, if we have a single log with a product inside it, you can write it as a log plus a log. Right, of the two, r and s would be the two factors of that product. So that's where it saves you time if you're doing really large arithmetic, right? If you have, 5 times 10 to the 8th power, instead of having to do the common log of 5 times, like, it's kind of a lot of talking. But if you had the common log of 5 times 10 to the 8th power, and this is before you have a calculator, right? Maybe you have a table of values. Well, probably, what's that going to be? 500 million, right? That's a big number. You probably don't have that in your table. Well, you could use this property to write it as the common log of 5 plus the common log of 10 to the 8. Right? We could look that up in a table. What is the common log of 10 to the 8th? Think back to your other properties. The base matches the base of the exponential. They cancel. This is just going to be plus 8. Right? This is going to be some number less than 1. So then what you can do is you can work with that small decimal number, and then you can convert it back, make it a power of 10. We don't have to do that, but that's where they originally came in useful. Here we have, if you have the log base b of a quotient, you can do the log base b of the numerator minus the log base b of the denominator. Again, you took something complicated, you made it simpler. This one's like, in terms of doing the math, log base b of r, so a base raised to a power, you can actually just take the power and put it out in front as a multiple. Okay, so it saves you like an order of magnitude. Instead of multiplying, you get to add. Instead of dividing, you get to subtract. Instead of doing an exponent, you get to multiply. So it's a pretty good deal there. So some examples here of condensing, which again, when we look at equations here tomorrow or whenever I see you next, would condense a lot. You would generally want to get a single log, and it's easy to solve. So in this case, we have a common log of x plus the common log of 5. Pretty straightforward, hopefully, right? That's an example of this right here. So we can go ahead and write as a single common log of 5x. I went ahead and put parentheses there to really emphasize that 5x is the argument, but you wouldn't have to. You could just write 5x, it'd be fine. Is that good? Here's a couple natural logs, 2 times the natural log of x minus 3 times the natural log of y. We see it is subtraction, so you start to think about quotient. Now what you want to be careful about is these definitions, these top two, notice there's no multiples here on any of these logarithms. That's because there can't be. You have to deal with those. So the third rule tells us if there is a multiple, you can bring it inside as an exponent. So here, a couple-step process. We would say the natural log of x squared, right? So that multiple out front comes inside as a power, minus the natural log of y cubed. So now we have a log minus a log. There's no numbers out in front. So we could say this would be the natural log of x squared over y cubed. We'd have a single logarithm. This last one, some people would argue this is already condensed. I think we're going to be better, though, to not have the 1/5 out in front. We want to go ahead and move that inside. So we will get the log base 4 of x to the 1/5, which is fine. You might see this a lot as the log base 4 of the 5th root of x. Does that work for us? Okay, so a lot of times when we're actually performing calculus, we're going to want to expand as opposed to condensing what we just looked at. So here are just a couple simple examples, I hope. The one thing to that we have to be careful about, which I didn't put here, is, these, if you have addition and subtraction, it kind of makes it weird. You got to keep those clumps together, and we'll probably run across something like that. But here we have the natural log of 9y. That's a product. There's nothing out in front touching it, so we can say that'll be the natural log of 9 plus the natural log of y. The next one, we have a common log of xy cubed. That's almost the same problem, right? Not too much going on there. We will get the common log of x plus the common log of y cubed. I know why I did that. Now, hopefully you're not tempted to pull the 3 out to start, but notice the cubed is only hitting the y, right? So notice here, the power has to hit everything in that argument before you can pull it out. So we have to split it. Now once we split it, now the cubed isn't hitting everything inside there. So now we can say the common log of x plus 3 times the common log of y. That's all log e. The next one here, we got a couple options. You could do a quotient right away. We could, though, realize that both the numerator and denominator are both to the 1/3 power. So if you wanted to, however you do it, you should arrive at the same answer. But let's say that we kind of imagine this as the cube root of x over y is just as valid, right? We just rewrote the radicals here. So in this case, you could say 1/3 natural log of x over y. And I wanted to do it this way to show you a potential mistake you got to be careful about. We know that we have a quotient inside a logarithm, so we can write it as a difference of 2 logs. But since the 1/3 is multiplied by the original logarithm, it's going to get multiplied by both pieces. So generally the way you just want to show that is 1/3 parenthesis natural log x minus natural log y would be fine. That's great. If you wrote 1/3 natural log x minus 1/3 natural log y, that's great also. Just to be careful, because really, as we get more and more definitions and properties, you really want to say, what is it saying, like we talked about. Look, there's no numbers out in front here. So if there are, this rule doesn't work. You got to deal with that first, those sorts of things. Okay, our last piece of kind of log info for today is called the change of base formula. Super useful, especially if you don't have a calculator where you can change the base on. So the main reason most people would use it, well here, let's look at the property. We start with the log base b of x. Again, b just has to be positive and can't be 1, right? X has to be a positive number like what we're used to. It says that you could rewrite that as the log base a of x, notice x was the argument, divided by the log base a of b, and notice b was the base. We changed the base with the change of base formula. Your question might be, well, what's a have to be? A can be anything you want. Okay, now, because your calculators have a base 10 common log and a natural log or base e, you probably want a to be the new base, a, the new base. Most times, you'll want to use 10 for a common log or e for a natural log. Usually people use 10 if it seems to make more sense to them, but as we get into calculus, you're going to start using e more and more. To the point where my Calc 1 professor in college, he would talk about logs. But anytime you just assumed it was a natural log. Like, you know, they said log, they meant natural log. If you go to like some computer software, if you type in log and Wolfram Alpha, it makes it a natural log because that's just what we tend to use. 10's an arbitrary number. We count at base 10 probably because we have 10 fingers. It's probably the main theory. E is actually called the natural base, and it has a lot of natural important things about it. So a lot of times, though, you may first use this as suppose you're asked to find what's the log base 17 of 1,000. I don't know my powers of 17, but I'm betting that 17 times itself is never going to be 1,000. So I wouldn't do that. So what you would do to evaluate this is you would either use the common log or the natural log and just type it in your calculator. So the natural log of 1,000 divided by the natural log of 17, you would type that in your calculator. Do make sure that you put that in parentheses. And that just to be good. I don't know what it is. I don't have a calculator with me, but there you go. That's how you would evaluate that if you didn't have a change of base button. We just want to practice here writing just using natural logs. So here, log base 4 of x, well, you would say the natural log of x divided by the natural log of 4. Okay, for our purposes in the future, The natural log of 4 is a constant, and we're going to see constants have a lot of really shortcut properties that we're going to be able to use, and then we can just deal with the natural log of x and then times a constant, which is not a big deal. Constants are easy to deal with. Okay. The next one here is the log base 1/3 of x minus y. You don't see fractional bases a lot, so we'll kind of maybe look into that, how we can switch them around. But if we're going to just write this using natural logs, it would be the natural log of the argument, which is x minus y, over the natural log of 1/3, which is fine. That's fine for us. Now, what you will see sometimes in that case, be aware, this numerator, we can't do anything with it. We had no properties earlier that said what to do if you have subtraction inside a logarithm. We said if you had division, you could subtract 2 logs, right? And in this rule, before when we had division, it was inside the argument, right? Where now it's the division of 2 logs. But a lot of times what you'll see here, instead of writing a log of 1/3, is 1/3, but this is an intermediate step, but 1/3 will be written as 3 to the negative 1 power. Right, we all know that, right? Like negative. And then what you can do is, since this is an exponent, you can pull it outside. So that will give you the log of x minus y over the opposite, the natural log of 3. That's a lot of errors, isn't it? But so you probably see this as the opposite of the natural log of x minus y. Usually you wouldn't leave the negative in the bottom. So you could either write it like this, with the negative out in front, or the negative up in the numerator. I don't really have a problem with this, but it's just sort of an interesting thing. Oh, another thing to notice here is if you do look at the rules, that's the same as the natural log of 1 minus the natural log of 3. And any log of 1 is always 0, correct? So this is just 0 minus the natural log of 3, which is minus the natural log of 3. So that's the change of base. Now that we know those properties, earlier I mentioned that I gave you an example that we didn't have a great way to do, but we figured it out because we're hard workers and we didn't give up. But we had the common log of 1 over the square root of 1,000. Okay, now that we know our properties, we can do a lot of different stuff with this, which actually makes it a lot easier to simplify this. First thing I've realized is, hey, there's division inside there, right? So because of that, we could say the common log of 1 minus the common log of the square root of 1,000. And what is the common log? This is a common log. What's common log of 1? 0. Now, could I pull this power out here? I could, right? So I could say 1/2 times the common log of 1,000. Right? Now you might we talked about counting zeros before, but also you could say negative 1/2 common log of 10 to the 3rd power. Right? This is one of our properties, is when the base matched the base of the argument, is they would just cancel, correct? So you see that we get negative 1/2 times 3 and negative 3/2, like we did before, but a completely different way before. Right? So you're going to get a lot out of logarithms if you just goof with them and you find different ways to get from A to B. Like just how did this property apply? How could we do this? Or we look at what occurs there. So it's really a case, I think there's quite a few problems actually I have for you tonight, so I'll get those posted.